Good afternoon, everyone. My name is Calderon. I'm your Group 4 reporter. Today, I'll be talking about the gas turbine electrical generation system. Our presentation outline. First, we'll begin with our experiment introduction, our thermodynamic relation, our objective, analysis, and then our results, followed by our conclusion. So our experiment introduction, pretty much the process, just kind of wanted to go over it. We're pretty much intaking air into our compressor. From there, we'll get a high pressure increase. From there, it'll enter our combustion chamber, which will then enter our power turbine. From our power turbine, that will produce a thrust, which will be deflected to our free turbine, which is connected to our alternator by a shaft. So that free turbine and that shaft that's being spun is going to generate power with our alternator. Our operational system concludes of number 1, our master switch that's keyed. Number 2, our green start button. Number 3, our red stop button. Number 7, 8, and 9 are our digital displays. Number 7 displays our temperature inlet for our turbine. Number 8 displays our engine rotational speed. And number 9 displays our generator turbine speed. And number 4 is our T-handled power lever, which is our thrust control. And number 5 is our load lever, which is also our brake. Next, I'll be talking about the sensors and why the sensors are important. So each sensor is placed before and after each different main component in our system. So that will be compiled to 5 stages. Stage 1 is our compressor inlet. Stage 2 is our compressor exit. Stage 3 is our turbine 1 inlet. And stage 4 is our turbine 1 exit and turbine 2 inlet. Stage 5 is our turbine exit for our free turbine. So in the bottom photo, it's a live screenshot of our software during the experiment. Each stage is color-coded and shows the temperature and pressure at that stage. As well, to the right side of that bottom photo, it shows the amount of power that we are generating. Next is our fuel content. So we are using kerosene as our fuel. Some advice for kerosene are for its energy content is 10.35 kilowatts hours per liter. Kerosene density is 0.81 grams per centimeter cubed. And the photo to the right is a jet engine being refueled with kerosene. Next is our thermodynamic relation. So in the top left dotted diagram, we have stage 1, 2, and 3. Our compressor, which is compiled of our compressor, our combustion chamber, where we have Q being added, and then our turbine 1. So that is also known as the Brayton cycle, as some of you may remember from thermodynamics. Next, I'll enter our right side diagram, turbine 2, our free turbine, that's connected to our alternator. Work is being put in from the shaft, from the free turbine, and then we'll get our power output. Next is the TS diagram and the PV diagram. As we can see, S1 is equal to S2, meaning that stage 1, stage 2, it is isentropic, as well as stage 3, stage 4, and stage 5, that as well is also isentropic. We have 2 constant pressure stages happening at a time, that it will be stage 2 and stage 3. Other constant pressure stages will be stage 1 and stage 5. So what we're trying to do, we're pretty much trying to gain an understanding of this turbogen electrical generation system. We're going to see how the power turbine and how the load, the optimal, at the optimal point where we can generate the most power. Similar to a car, how we want to find the best fuel economy by not using our gas efficiency so much, and as well keeping it at the right RPM. So in the orange circle is our power that's being shown in our turbogen software. Our analysis is next. So our stage 1, our compressor inlet is our compressor inlet temperature is roughly between 25 degrees Celsius and 32 degrees Celsius. Our compressor inlet pressure, it is slightly increasing and has a sudden decrease towards the end of our cycle, and that is because of our system shutdown. Our enthalpy value for stage 1 is coming to 299.4 kilojoules per kilogram, and that's found from doing CP times T1. Our stage 2 compressor outlet is also shown a increase of our outlet temp, as well for our exit pressure is also very similar to our compressor inlet pressure. Enthalpy value is 399.7. Stage 3, turbine 1 inlet. We see our temperature is slightly increasing, not too much, not too dramatically. Turbine 1 inlet pressure has the same pattern as before. Enthalpy value is shown. Stage 4, very, very similar as the previous stage. Stage 5, still very, very similar. Our fuel flow, we can see as our engine RPM increases, our fuel demand increases. Next up is our jet engine speed. So pretty much we want to keep our jet engine speed pretty constant at 40,000. And after a period of time, we'll increase to 50,000. And then next will be 60,000 and then 70,000 to finish. We can see our maximum power generated in the bottom photo is around 90 watts. And that's coming from our max engine speed and our generated turbine speed also, as well being the maximum. Our power, again, is around 90, and that's around 15.753 seconds near the peak. And we can see our voltage and our current is roughly very similar in regards to time. And as well, the maximum voltage and current results in our maximum power, just because that's proportional. Power is proportional to voltage and current. We were known that square root of 3 times our voltage and current will give us our power. Here are the average, max, and min values of each value shown. Our peak power analysis. So we're going to use these values for our system performance, just like a normal engineer would do in their career. Again, maximum voltage and max current equals our max power generated. And so our max power was actually 90.949 watts. Analysis, our work of our compressor, our energy supplied, our turbine speed, power turbine specific work, our power turbine specific work cycle. Our efficiency of our power cycle comes out to be 10.52%, and our free turbine specific work is also displayed. In conclusion, 10.52% efficiency is actually fairly low compared to an actual peaker plant, which is where this system would be used for. And a peaker plant, we would probably get around 20 to 42%. And so that pretty much tells us that our system is pretty inefficient, probably because of our fuel. And as well, at max engine speed, that will produce our max current through our resistive board, which will give us our power generated. Here are my references, and that is all. Thank you.